What is the advantage? If you look at this data set, suppose the data, the patterns in the data is like this. When you apply something called as linear regression, it will capture this line. This curve will not get captured. The patterns in the line gets captured when you use something called as linear regression. Okay. And here you have a nonlinear pattern. If you have a curve like that, it is called as quadratic pattern. Quadratic pattern or polynomial with 2 degrees. If I have a curve like this, how many bends do we have? 2 bends. So it's called as polynomial with 3 degrees. Here you have a single bend, so polynomial with 2 degrees. You have 2 bends of polynomial with 3 degrees. Sorry. So in order to capture the patterns in this, you have to run a polynomial regression with 2 degrees, which will be like this. Y regress upon x and x squared. So you take the highest value square. Here you just say x. If you run only this algorithm, it will not be able to capture this pattern. If you run only this algorithm, it will capture only this pattern. Straight line pattern is not captured. If you want the patterns pertaining to this, this, and this, then I need to stack these two together. In these kind of scenarios, stacking will be helpful. When your underlying data has both linear patterns and nonlinear patterns, if you want to capture both, then you go with stacking. Because in stacking, we are going to use different algorithms. So one algorithm will capture one pattern, another algorithm will capture another pattern. When you combine those two, both the patterns will get captured. So if you look at the dots, right, that is the actual data. If you use linear regression, only that red line to capture that. If you use only nonlinear or polynomial with 2 degrees, this kind of a pattern will get captured. If you want both, you need to combine them using stacking. So both linear and nonlinear kind of relationships get captured when you have stacking. Okay. And whenever you use algorithms, try to use different set of algorithms altogether, which work very differently. If you have algorithms which work very differently, they'll capture very different patterns. If you use all decision trees, all the trees will more or less capture same kind of information, right? They work in a similar way. If everyone starts thinking in a similar fashion, you get the same ideas. But if you have people from different thought process brought in, they'll think differently. That's the idea. So you have logistic regression, which will work differently. KNN will work differently. Support vector machine will work differently. All these three algorithms have different ways of capturing the patterns in the data. When you apply logistic regression on the data set, okay, and then when you use this model to predict, what will you get? Predicted values. Let me call those as P. When you run KNN algorithm on this data set, and then when you predict on this, you get P2. When you run support vector machine algorithm on this data set, and then when you use this to predict, you get P3, and then you have your output P2. Here also, see, on this data set, you run logistic regression, you run KNN, you run support vector machine, you get the predicted values, and then take the output value from here. Now run random forest on this, run gradient boosting on this. When you run gradient boosting on this and build a model, and when you use that model to predict on this, what do you get? Predicted values pertaining to this algorithm. When you use random forest and build a model on this, when you again test this model on this, you get the predicted values. Take the output variable from here. Now use this and build some other algorithm. In that way, you can put as many stacks as possible. Stacking, grouping, how many ever meta learners you want you have. So the algorithms at this stage are called as what? All these base learners. When you combine the results of the base learners, what do you get? Meta learners. From there on, when you combine the results of set of algorithms, they are only called as meta learners. Okay. So that marks the end of our set of algorithms. We could successfully understand voting, stacking, bagging, boosting, and random forest. Within boosting, ADA boost, gradient boosting, extreme gradient boosting. Now our goal is to run all of those algorithms. The object of stacking, boosting, observation. Yeah. The moment you get into ensemble techniques, one thing should be clear that your goal is to increase what? Accuracy and stability. Because you want more or less the accuracies to be constant. Just because you changed the training and test data doesn't mean your accuracy should vary drastically. Right? So from that standpoint, stability and accuracy will be high. Any algorithm, any ensemble algorithm, that's the goal. But what is the price that you pay for that? You lose interpretability and time consuming.